Hey everyone, welcome back to another lesson. This video will cover prime numbers, composite numbers, and numbers that don't fit in either of those categories. We'll then dive into prime factorizations and a foolproof way of finding every factor of a number. At the end, we'll solve our way through a couple application problems as well. Here are the timestamps for this lesson. If you're looking to review some specific concepts or examples, you can jump right to them here. There are four main objectives we want to cover in today's lesson. Number one, we want to be able to tell the difference between prime and composite numbers versus numbers that don't fit into either category. Number two, we want to be able to determine the prime factorization for any of our whole numbers. Number three, we want to be able to use our prime factorizations to make complete factor lists. At the end, we'll do a couple word prompts together to see if we can apply these concepts. Let's get into it. Here are the vocabulary words that we're going to be using today. The first one is divisibility. The second one are factors. Next, we have prime. After that, we're going to talk about composite numbers. And then later, we'll talk about prime factorization. While you may have heard of these words before, we're going to dive a little deeper into the concepts so you understand exactly what to do with them. Big picture, I want you to first understand that we're going to be talking about the world of whole numbers here. Whole numbers are just numbers that are 0 or higher. We're not going to consider any fractions, any decimals, or any numbers in between these, and we're also not going to consider negative numbers. An overarching concept that you want to leave this lesson understanding is how we can sort these numbers. All the whole numbers from 0 and above can be categorized as either a prime number, composite number, or a strange number. I'm going to call them Stranger Thing numbers here. Let's get the first two out of the way. 0 and 1 are the only two numbers that fit into the Stranger Things numbers category that behave a little differently than all the other numbers that are higher than it. The reason why 0 is a little bit strange is because 0 has infinite factors. 0 times anything is going to be 0. The reason why 1 is a little strange is because it only has one factor, 1. Now that we got the two strange numbers out of the way, let's talk about the rest of them. These will all fit into either the prime category or the composite category. 2 is prime, 3 is also prime, Now keep in mind, we only sorted the first 15 numbers. We do want to ask ourselves, why? Let's dive a little deeper into these concepts. Before we talk about prime and composites anymore, we do need to discuss divisibility rules. Do you know how to tell if a number is divisible by another? Knowing the divisibility rules between 1 through 10 are going to save you a ton of time throughout this course. These tricks will help you avoid doing long division if you can help it. The first one's easy. 1 is a factor of every number out there. Therefore, all numbers are divisible by 1. Next, how do we know if a number is divisible by 2? Well, if it ends in an even number like 0, 2, 4, 6, or 8, then it's going to be divisible by 2. Then there's 3. This one is the first one that gets kind of cool. It turns out if the sum of the digits is divisible by 3, then the whole number is divisible by 3. For example, if you add up 1 plus 1 plus 1 here, you get 3. 3 is divisible by 3, so 111 is divisible by 3. 111 divided by 3 is 37. Off the top of your head, you might not have known that 57 was divisible by 3. Well, since 5 plus 7 is 12, it's divisible by 3. 57 divided by 3 is 19. To see if a number is divisible by 4, just look at the last two digits of each number. If the last two digits create a number divisible by 4, then the whole number is divisible by 4. Another way you can think about this is, if you can divide the number by 2 and then divide by 2 again, then it's divisible by 4. Something to note here is that if you can't divide it by 2, you definitely can't divide it by 4. This one's a crowd favorite. In order for a number to be divisible by 5, it needs to end in a 5 or a 0. This one's pretty neat too. For a number to be divisible by 6, it has to be divisible by 2 and 3. So if it doesn't work for 2 and it doesn't work for 3, it definitely doesn't work for 6. It needs to work for both of them here. This is the strange one on the list. While I could tell you a rule on how to do this, it's a little bit more complicated than all the other ones. To be honest, just using standard algorithm for long division is probably going to be faster. Now 8's rule is a little bit similar to 4's, except we're going to look at the last 3 digits instead. If the last 3 digits are divisible by 8, then the whole number is divisible by 8. If that's confusing, you could also see if you could just divide the number by 2 3 times. So if you can cut a number in half, then cut it in half again, and cut it in half one more time, then the original number is divisible by 8. That hopefully makes sense because 2 times 2 times 2 does get you 8. That brings us to 9. 9's rule is very similar to 3, where you add up all the digits. Here, if you add 4 plus 0 plus 5, you get 9. If that number, or that sum, is divisible by 9, then the whole thing is divisible by 9. Let's end on an easy one here. How do you know if a number is divisible by 10? Well, this one's pretty picky. The number just has to end in a 0. So if the number doesn't add in a 0, it's not going to go in evenly. In a little bit, you're going to see how we're going to apply these rules, but they're here in case you need them. Let's briefly talk about prime numbers. A prime number has exactly two factors, one in itself. What's a factor again? A factor is just a number that multiplies to get you the number. Here you can see a list of the first few prime numbers in the world. 2 is super special because it's the only prime number that's even. Every other prime number is going to be odd. So why is 2 prime? Well, the only way to get 2 through multiplication is 1 times 2. There are no other numbers that multiply to get to 2. If you consider 3, the only way to get 3 through multiplication is 1 times 3. This rule holds true for all the other prime numbers on this list. You can even try it for yourself. Think through the factors of 5, or 7, or 11. And if you can't think of any numbers besides 1 in itself as a factor, then it's got to be prime. It's important to remember that while almost every prime number is odd, 2's the exception. Now that we've talked about prime numbers, let's talk about composite ones. All composite numbers have more than 2 factors, but a finite amount. While it could have 3 or 4 or 5 or even 10 or 20, it can't have an infinite amount of factors like 0 does. Here are some examples of composite numbers. 4 is composite because we have the factors 1 times 4, but we also have 2 times 2. It has 3 factors. 6 is composite because we have 1 and 6 and 2 and 3. This one has 4 factors. 8 has the factors 1 and 8 and 2 and 4. As you see, all the numbers on this list are going to have more than 2 factors. A common misconception that students have is that composite numbers must be even. If you look at this 9 here, even though it's odd, it's composite. Not only do we have 1 times 9, but we have 3 times 3. 9 has 3 factors, making it composite. In addition, while 15 is an odd number, it is also composite. Not only do we have 1 times 15, but we have 3 times 5. 15 has 4 factors, making it composite. Remember, there are infinitely many prime numbers in the world and infinitely many composite numbers as well. So, is every number prime or composite? Well, no, there's a couple exceptions I want to talk about real quick. Remember, prime numbers have exactly 2 factors, no more and no less. And composite numbers have more than 2 factors, but a finite amount, meaning you can't have an infinite amount. That brings us to our 2 exceptions. Our first exception is 1. The only factors of 1 are itself. While we say 1 times 1 is 1, it only has 1 factor, 1. And the second exception is 0. The reason why 0 doesn't get to be prime or composite is because it has infinite factors. Think about it real quick. We could say 0 times 1, we could say 0 times 2, 0 times 3, and 0 times 4, and so on and so forth, right? We can go on forever with the factors. While composite numbers have a finite number of factors, 0 has an infinite number of factors. So at this point, we've talked about prime numbers, composite numbers, and numbers that don't fit into either category. That brings us to prime factorization. It turns out every number can be broken down into a multiplication sentence with only prime numbers that result in the given number. We typically think of prime numbers as the building blocks or the Lego pieces that build up all the other numbers in the world. You could also think of prime numbers as the DNA of numbers. Since these prime factorizations only consist of prime numbers, we'll never use 0 or 1. Let's look at a few examples here. We'll start off with 12. If we look at the prime factorization of 12, it's 2 times 2 times 3. These are all prime numbers and they result in 12. If you want, you can use exponents to write it a little bit shorter. To show you how to get prime factorizations, we use a strategy called factor trees. You take the original number 12 and you think of 2 numbers that it breaks down into. While you may think of 1 times 12, remember, we can't use 1 since it's not prime or composite. That leaves us with 2 and 6 or 3 and 4. It doesn't matter which one you use, they'll both work just fine. I'm going to choose 3 and 4. Since 3 is prime, I'm going to circle it. Since 4 is composite, we know it could be broken down a little bit more. The 2 factors of 4 you should be thinking of are 2 times 2. Since these are both prime numbers, we're going to circle them. As you're doing prime factorizations, you should be only circling prime numbers. Let's review what the first few are. 2 are only even 1, 3, 5, 7, 11, 13, and 17. While there are infinitely more prime numbers out there in the world, these are the most common ones you're going to use, so I suggest trying to memorize them. I hope that you can see that the 2, 2, and 3 from our factor tree become the multiplication sentence for our prime factorization. Finding the prime factorizations for prime numbers is super easy. It's just the number itself. If you were thinking that you might have to write something like 23 times 1, think again. You can't use 1 in prime factorizations because it's not prime. So if you ever have to find the prime factorization for a prime number, just write the number itself. Let's look at the prime factorization for a slightly larger number here, like 80. As you can see here, the prime factorization for 80 is 2 times 2 times 2 times 2 times 5. Using exponents, you can say 2 to the 4th power times 5. Understanding and being able to write prime factorizations well is going to help you a lot in future lessons. Now that we've done an overview on a bunch of these topics, let's actually try using them in some examples. To get the most out of these videos, I suggest taking out a piece of paper and something to write with to do some of these with me. To keep this interactive, feel free to pause, rewind, and fast forward to any parts that are more useful to you. In example 1, we're going to identify whether numbers are prime or composite. To prove whether 9 is prime or composite, we have to identify how many factors it actually has. Well, we can start off by saying we do know that 1 times 9 is 9, so it has 2 factors. But are there any other ones out there? If you've thought of 3 times 3, then that's really good. Here we can see that 9 has 3 factors, 1, 3, and 9. Since it has more than 2 factors, 9 is composite. Let's look at the number 31 here. We should always start off with 1 and know that 1 times 31 is going to be 31. But are there any other factors? At this point, it's important to go through your divisibility rules and see if you can divide it by any other number. If you're convinced that it's not divisible by any other number, then you can say it's prime. 31 only has 2 factors, so we can conclude here that 31 is prime. What about 57? We can start off by saying we know that 1 times 57 is 57. But does it have any other factors? Well, we know it isn't divisible by 2 because it's an odd number. But how about 3? If you add the digits up 5 plus 7, you do get 12. Since 12 is divisible by 3 and it equals 4, then we know we can divide 57 by 3 as well. It turns out 3 times 19 is also 57. At first glance, 57 could look like a prime number, but using divisibility rules uncovers that it's actually a composite. 57 has 4 factors, making it a composite number. What about 24? If you want to try this one on your own, feel free to pause it and try it, but I'm going to go through it with you as well. We can start off by saying we know 1 times 24 equals 24. But we also know that 2 times 12 is 24. Even though we already know it's composite, I'm just going to write the rest of its factors. 3 times 8 is 24, and also 4 times 6 is 24. In this case, we can see that 24 has 8 factors. Since 24 has 8 factors, it's a composite number. At this point, I'd like you to try and prove to me whether 27 is prime or composite. Make a complete list of factors and decide whether it's prime or composite. It turns out 27 is a composite number. It has 4 factors. Pause the video again and try to list the factors of 111. Decide whether it's prime or composite. Even though 111 looks prime, it's actually composite. If you use the divisibility rule, you can see it's divisible by 3. Pause again and give this a try. It turns out 48 has 10 factors, definitely making it a composite number. And one more. See if you can list all the factors of 23. Turns out 23 is prime. It only has 2 factors. 23 is a prime number. Now that you've gotten a little better at identifying prime and composite numbers, let's try writing prime factorizations together. Remember, the most common prime numbers you should be using in these prime factorizations are 2, 3, 5, 7, 11, 13, and 17. While this list does go on, these are the most common ones you're going to see. To help you get started, I've listed 7 of the most common prime numbers used in prime factorization. To find the prime factorization for 36, we're going to make a factor tree. We'll start off by writing 36 and break it down into 2 numbers. The first thing that comes to mind for me is 6 times 6. Since 6 is a composite, we know that we can break it down further. 6 is the same thing as 3 times 2. This 6 can also be broken down into 3 times 2. Here's how we circle the prime numbers. The product of these circled numbers, or these prime factors, is going to equal 36. To write our prime factorization for 36, we can write it as 2 times 2 times 3 times 3. If you want to use exponents, you could say 2 to the second power times 3 to the second power. Let's try another one. Let's see if we can find the prime factorization for 17. Well, first of all, we can write 17 in our box here, and we have to think about factors of 17. So since 17 is a prime factor, we actually just write the prime factorization for 17 is just 17. It can't be simplified in any way. Let's try a third one together. Let's write the prime factorization for 72. Start off by writing 72 at the top and think of 2 numbers that multiply to get 72. The first thing that comes to mind for me is 9 times 8. Again, if you think of other numbers, that's perfectly fine. See if we get the same answer. I know 9 breaks down into 3 and 3 because it's a composite number. And I know 8 breaks down into 2 times 4. The only number here I see that can be broken down further is this 4. 4 is the same thing as 2 times 2. Again, at this point, we circle all of our prime numbers at the bottom of the tree. The prime factorization for 72 is 2 times 2 times 2 times 3 times 3. Using exponents, we can say it's 2 to the third power times 3 to the second power. Let's try to find the prime factorization for 96 now. I'm going to start off by writing 96 and think about 2 factors that go into 96. If you're stuck and you're not sure what you can divide 96 by, try using your divisibility rules. Since 96 is an even number, we know we can divide it by 2. Turns out 2 times 48 is going to be 96. If you can't think of factors that go into the number, you can always try doing long division. Since 2 is prime, I'm going to leave it alone, and I can break 48 down into 6 times 8. Since 8's composite, I can break it down further. 8's going to break down into 2 times 4. And 4 can break down into 2 times 2. The 6 over here is also composite, and I can break that down into 2 times 3. It turns out the prime factorization for 96 is 2 times 2 times 2 times 2 times 2 times 3. To use an exponent, we can write this as 2 to the 5th power times 3. Now it's time for you to practice. Pause the video and give this one a try. Unpause the video when you're ready to check your answer. The prime factorization for 45 is 3 times 3 times 5, or 3 squared times 5. Now try finding the prime factorization for 60. The prime factorization for 60 should be 2 times 2 times 3 times 5. Using exponents, we can say it's 2 squared times 3 times 5. And let's try another one. Here I want you to find the prime factorization for 57. If you think it might be prime, think again. This one is actually composite. Think about your divisibility rules. The prime factorization for 57 is just 3 times 19. Let's try one last one of these together. Find the prime factorization for 100. The prime factorization for 100 is 2 times 2 times 5 times 5, and you can say this is 2 to the 2nd power times 5 to the 2nd power. Here in example 3, we're going to use the prime factorization to try and list all the factors of a given number. Let's try a couple together here. First, we're going to write the prime factorization out. It turns out 72 has a lot of factors. How do we know if we've gotten them all or not when we're listing them? Well, we should start off by writing 1 times 72, right? Every single number has those factors, 1 in itself. One of the most frustrating parts about finding factors of a number is doing long division. My trick for you today is going to be about using the prime factorization to use multiplication instead of long division. The fact that we see 2 on our prime factorization list means that 2 has to be a factor of 72. Since we know 2 is a factor of 72, we'll add it to our list here. It turns out 3 is also a factor of 72 because it's on the prime factorization list. Now, is 4 a factor of 72? Well, even though you don't see a 4, you can actually create a 4 by multiplying 2 of these 2's together. 4 is a factor of 72. What about 5? Do you see 5 on the list here? No. Also, can you multiply any 2 factors here to get 5? Nope. So 5 is not a factor. What about 6? I don't see 6 on the list, but can you multiply 2 factors to get 6? Well, since 2 times 3 does get us 6, 6 is a factor of 72. What about 7? Well, 7's a prime number, and if it was a factor, it would be on this prime factorization list. What about 8? We don't see an 8, but can we get 8 through multiplication? Turns out if you multiply these 3 2's together, you do get 8. 8 is a factor of 72. So we know that 2 is a factor of 72, but 2 times what is 72? Instead of doing long division, we can actually just multiply the rest of the prime numbers here to get us our other factor. 2 times 2 is 4, 4 times 3 is 12, and 12 times 3 is 36. Turns out 2 times 36 is 72. How about 3? Well, we know 3 is a factor, but 3 times what is 72? So 3 times what is 72? You could do 72 divided by 3, or you could multiply these numbers to get that other number. So if you get 2 times 2, that's 4, 4 times 2, that's 8, and times 3 is going to be 24. It turns out that 3 times 24 is 72. What about 4? 4 times what is 72? Instead of doing long division, let's take a look at the rest of these prime numbers here. 2 times 3 is 6, and 6 times 3 is 18. It turns out 4 times 18 is 72. That brings us to 6. 6 times what is 72? Well, if we multiply these leftover prime numbers, 2 times 2 is 4, and 4 times 3 is 12, we know that 6 times 12 is 72. Now let's look at the 8. If you know your multiplication fact, you probably knew 8 times 9 was 72. But if you take a look here, that confirms it that 3 times 3 does get us 9. Since there are no numbers between 8 and 9, we can stop here. If we kept going, the factors would just reverse themselves. We would then get 9 times 8, 12 times 6, and so on and so forth. Changing the order of the factors doesn't mean they're new factors. Here we can see that 72 has 12 factors. Let's try this again with the number 48. First, we're going to expand the prime factorization to write 2 times 2 times 2 times 2 times 3. Next, we're going to think of what factors of 48 do we start with. Well, we always start with 1 and 48. What's next? Well, we see a 2 on our list and we see a 3 on our list. We should write both of those down. If we know that 2 is a factor, we can box the rest of the prime numbers to find out what the other factor is. 2 times 2 is 4, 4 times 2 is 8, and 8 times 3 is 24. Hopefully this makes sense that 2 times 24 is also 48. 2 times 2 is 4, 4 times 2 is 8, and 8 times 2 is 16. 3 times 16 is also 48. What's next? Is there a 4? Well, we don't see a 4, but we can get it with two 2's. Besides the two 2's, we have this 2 times 2 times 3, which happens to be 12. 4 times 12 is 48. What about 5? 5 is a prime number, so it would be on this list if it was part of it. So we're going to skip it. Let's move on to 6. Well, 2 times 3 is 6, so 6 is definitely a factor. If the 2 and the 3 make a 6, we should look at the leftover primes here. 2 times 2 is 4, 4 times 2 is 8. Hopefully you knew that 6 times 8 is 48. So why did I know I could stop at 6 times 8 and that I was going to be done here? Well, the only number between 6 and 8 is going to be 7. Since we know 7's not going to be a factor because it's not on a prime factorization, we can stop. 48 has 10 factors. Now it's your turn. I'd like you to pause the video and try to find all the factors of 96. Start off by expanding the prime factorization and give it a go. Here you can see that the different combination of prime factors help us create the entire factor list for 96. There are 12 total factors. And let's try finding all the factors of 180 using the prime factorization. Pause the video and give it a try. Check this one over carefully. There's 9 factor pairs making a total of 18 factors. Now in example 4, I'm going to teach you a little trick that not a lot of people know about. You can use the prime factorization of any number and figure out the total number of factors. Let me show you. Let's look at the number 96 here. 96 is how many factors? Well, from earlier we found out that it had 12 factors. But if you wanted to check to see that we got them all, I have a neat little trick for you. The prime factorization represents that there are 5 2's and 1 3. I'm going to just write the 1 here so you can see it. All you need to do here is you take the 5 and just add 1 onto it. You take the 1 and add 1 onto that one as well. If you take these numbers, 5 plus 1 is 6, and you multiply it by 1 plus 1, which is 2, you're going to get the total number of factors that 96 has. So, does the trick work over here? We have 2 to the 4th power, and we just add 1 onto its exponent. 4 plus 1 is 5. There should be 5 factors. Let's try another here. So earlier we did 180 and we found out it had 18 factors. Let's see if this little trick works here as well. Again, this 5 has a little 1 up here. This 2, let's add on 1. This 2, let's add on 1. And let's add on 1 to this one here. 2 plus 1 is 3. 2 plus 1 is 3. 1 plus 1 is 2. If you multiply these together, we get 18. There are 18 factors. Let's just try one more before you give it a go. All right, so 360 is going to have a lot of factors. How many though? Let's figure it out without doing a lot of work. First, we realize just 1 5, so we'll write that in. We'll take this 3, we'll add on 1 to it. We'll take this 2, we'll add on 1 to it. We'll take the 1 and add on 1 to that here. 3 plus 1 is going to get us 4. 2 plus 1 is going to get us 3. And 1 plus 1 is going to get us 2. If you multiply these all out, you would get 24. So there are 24 factors of 360. Now it's your turn. Pause the video and write down this prime factorization. See if you can determine how many factors 80 has without even listing them out. If you got 10, good job. If you want to check it, go ahead and try listing all the factors of 80 out. You should get 10 of them. And let's try another here. It turns out 120 has 16 factors. Practice makes perfect. Try 63. 63 has 6 factors. And let's just try one more. How many factors does 2048 have? If you don't want to list them out, just use its prime factorization. 2048 has 12 factors. That brings us to example 5. In example 5, we're going to be doing a couple application questions. We're going to apply our knowledge of prime factorization and factors in general to solve some real-world problems. I'd like you to pause the video and read the question to yourself, and then unpause it to go over it with me. First, it's important to note that we have a rectangular area for a dog to play in. Next, while we're not given the dimensions of the rectangular play area, we are given the area of it, which is 60 square feet. The question then goes on to ask how many whole number dimensions we can have for this rectangular play area. No fractions and no decimals. To figure out all the dimensions, we can use prime factorizations. I'm going to start off by making a factor tree here. Pause the video and try making a factor tree. The prime factorization for 60 is 2 times 2 times 3 times 5. When we start listing factors of 60, we always start with 1 times 60. If you look at your prime factorization, 2 is on the list, so we can add it to ours as well. If you cover up the 2 and look at the 2, 3, and 5, we know it's going to be 2 times 30. 3 is on the list, we'll write it down. If you cover up the 3, 2 times 2 times 5 is going to be 20. Well, there's no 4, 2 2's make a 4, so we'll have a 4 on the list. If you cover up those 2's, 3 times 5 is 15. 4 times 15 is 60. 5 is on the list, so we'll write it down. 5 times what is 60? We'll cover it up. 2 times 2 times 3 is 12. There's no 6 on the list, but 2 times 3 does get you 6, so we can write a 6 down. And if you cover those up, 2 times 5 is 10. Now the only numbers left that could be between 6 and 10 are 7, which is not on the list, 8, which is also not, and you can't make it because you would need 3 2's. 2 times 2 times 2 is 8, and 9. But to make 9, you would need 2 3's in our prime factorization, and we only have 1. Here we have all the possible whole number dimensions for this playpen. The next part of the question asks about perimeter. Since Mr. Lee has already bought 35 feet of fencing, he can't make a fence that is longer than 35 feet around. The goal here is to use the dimension from our list that maximizes the amount of fencing we have so we don't waste any of it. If you look at this option here, we notice that we're saying the length is 1 and the width is 60, or vice versa. If we made the length 1 and the width 60 here, then the perimeter would be actually 122. Again, that's all the way around the perimeter. That's way too much. We can cross this one off the list. Looking at this next option, that's still going to be way too much because if one side is 30, then the opposite side is also 30. That already goes over the amount of fencing we have. Since these are all so big, maybe I'll jump to the bottom here. Let's try this 6 and 10. If I make this one 6 and 10 and 10 and 6, what is that all the way around? It happens to be 32, so 32 could work. Okay, we'll keep that one on the side. What if we try going a little higher with the 5 and the 12? Well, 5, 5, 12, and 12. Well, 12 times 2, that's 24, and 5 times 2 is 10. 24 plus 10 is 34. Oh, wow. This one actually beats out the 6 and 10. It's even closer, so we would only lose 1 foot of fencing as opposed to 3. And what do you guys think about this 4 and 15? Well, we put a 4 here and a 15 here, a 4 here and a 15 here. 15 times 2, that's 30. 4 times 2 is 8. 8 plus 30, that's 38. Oh, that's a little bit too much. So I think we have our winner here. In conclusion, we should use the 5 by 12 dimensions to get the area of 60 while also using the most amount of fencing without wasting as much. Now here's the last example and practice problem of the lesson. I'd like you to pause the video and give this one a try. If you're experiencing some difficulty, I'd rather you skip back to the previous problem than to skip forward to the answer for this one. If you're still having trouble, then I suggest skipping forward to see the solution so you can understand the problem a little better. It turns out the farmer should have gone with a 6 by 16 meter fencing. At this point, I hope you're able to tell the difference between prime and composite numbers, how to write prime factorizations, and how to use them to write factors and solve real-world problems. Good luck, and I'll see you guys in the next one.